using our complex numbers to prove the trig identities that we've already seen some of them, but it's another way of proving them. So let's start with the two basic ones there, cos 2 theta and sin 2 theta, which hopefully we know by heart. Now that we've got Moivre's theorem, I can say, well, cos 2 theta plus I sin 2 theta is the same as cos theta plus I sin theta squared. Now if I expand the right hand side out, all I've got to do is equate the real and the imaginary parts, and we've got our trig identities. So if we look at the real part, cos 2 theta, cos squared minus sin squared, sin 2 theta, 2 sin theta cos theta. So a very quick proof. But of course that idea can then translate to any power. So let's look at sin 3 theta, cos 3 theta, and tan 3 theta as well. So now we'll be cubing it. So if you remember your perfect cube pattern, 1, 3, 3, 1. So there it is, 1, 3, 3, 1. But our I squareds we're converting to -1. And so a real part, sin 3 theta is, well, I suppose that satisfies the question because it's in terms of both sine and cos. If I wanted to make it all sine, then I'd change the cos squared to 1 minus sine squared. Did I do that? Yeah. Change the cos squared to 1 minus sine squared, and then you've got it all in terms of sine. Let's look at the imaginary. Cos 3 theta, again, that satisfies the question because it says in terms of sine and cos. But this time we'll change the sine squared to 1 minus cos squared. There it is in terms of the cubes. Now the tan, well remember tan is sine over cos. The one I'm going to substitute in is the very first one where it's a mixture of sines and coses. So sine on the top, cos on the bottom. Because if I want to turn each of those into tan, I basically need to get sine on cos. So if I divide by the highest power of cos, so whatever the highest power of cos is, then every one of those should simplify down to be sine on cos and to the same power, which it does. And so all of those sines on coses we can convert to tans, and there's our formula. 3 tan theta minus tan cube theta over 1 minus 3 tan squared theta. Show that cos pi on 9 is a solution. Well, I suppose the first temptation is to substitute it in. Unfortunately, pi on 9 is not one of our exact values, so it's a bit hard to do that. So let's have a look at our equation. 8x cubed minus 6x minus 1. I'm going to factorise it, but factorise it a little bit strange. I've only factorised the x cubed and the x. A reason? Well, given what we just saw with the trig identities. Have a look at the pattern for cosine. Let's just flick back there. Cos 3 theta, 4 cos cubed minus 3 cos. So 4 times something cubed minus 3 times something. Now have a look at how I factorise it. 4 times something cubed minus 3 times something. Same pattern. So if I let x equal cos theta, then inside the parentheses I now have that relationship we just proved. So I can say, oh, hang on, that's the same as cos 3 theta. And we now have a much simpler equation to solve. Cos 3 theta equals half. So we get pi on 3, 5 pi on 3, 7 pi on 3. We are looking for 3 consecutive solutions. Not only 3 consecutive solutions, 3 consecutive different solutions. That's why we've got to be careful with trig. Because we know things like, I'm using cos, but say I had sine. We know that the sine of 20 is the same as the sine of 160. So if 20 and 160 came up in our solutions, well hang on, they're the same solution because they would produce the same answer. Now that'd be fine if we had a double root, and this particular equation doesn't have a double root. You can always check that of course by differentiating and seeing if it's got a common solution. I know I need 3 distinct ones here. Divide by 3, there they are. Pi on 9, excellent, that's what I'm looking for. 5 pi on 9 and 7 pi on 9. I've probably done more than what they wanted, but I've ended up finding all 3 solutions. There you go, so that's what I was saying. 3 consecutive unique solutions. All right, so we have shown that, yes, cos pi on 9 was one of our solutions. Usually you find a follow-up question where you're now going to play with sum and product of the roots and things like that. Evaluate what cos pi on 9 times cos 2 pi on 9 times cos 5 pi on 9 is equal to. Well, we now know the 3 solutions Well, cos pi 9, 5 pi 9, 7 pi 9. But that's where we can play around with the trig. It's what I was just saying before. Hang on, cos 2 pi 9, that would be the same. It would give me the same answer as cos 7 pi 9. Let's do the product of the roots first. So alpha, beta, gamma is an eighth. There we go. So that root of 7 pi on 9, I'm going to exchange. But be careful, because I'm playing with cosine, second quadrant, it would actually be negative. So cos of 7 pi 9 would be minus the cos 2 pi 9. So therefore, substituting in, we now get that product is negative 1/8. So z is our standard complex number, which has a modulus of 1 in this case. They want us to find zn plus 1 on zn and zn minus 1 on zn. So z to the power of n, used above, so we'll get that. Now 1 on z to the power of n. There are different ways I could think of that. I could say, well, it's the reciprocal of what I just found. So I know it's the conjugate over the modulus squared, but remember the modulus of this is 1. So it's just going to end up being the conjugate. Or I could change it to a negative index, and we get the cos of negative n theta. And then we know cosine, well, that's an even function. Sine, that's an odd function. Once again, we end up with the conjugate. But either way, they're conjugates. So if I add conjugates together, then I'll be left with twice the real part. So I get 2 cos n theta. If I subtract conjugates, I'll get twice the imaginary part. So I have 2i sine n theta. This allows us to do some more playing. We're now going to express cos cubed in the terms of cos n theta, so multiples of theta. So 2 cos theta cubed, I could rewrite as z plus 1 on z cubed, because z plus 1 on z will be 2 cos 1 theta. Well, on the left-hand side, if I actually cube it, I get 8 cos cubed theta. On the right-hand side, I expand it out, but now I group the z cubed with the 1 on z cubed, so matching the powers, basically, or the size of the powers. But the z cubed plus 1 on z cubed, I can now go back to the formula, and that'll be 2 cos 3 theta, and the z plus 1 on z will be 2 cos theta. Multiply by the 3, we get 6. Careful though, it's so tempting to, when you do this, to go 2 cubed, because you're so used to cubing the modulus. It's not. This is always 2, and the other one's always 2i, even though we're changing the power. So cos cubed ends up being a quarter cos 3 theta plus 3/4 cos theta. All right, let's have a bit of a play.